In physics, special relativity is the accepted physical theory regarding the relationship between space and time. It is based on two postulates, that the laws of physics are invariant in all inertial systems, and that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source. It was originally proposed in 1905 by Albert Einstein in the paper on the Electrodynamics of Moving Bodies. The inconsistency of Newtonian mechanics with Maxwell unregistered trademark S equations of electromagnetism and the inability to discover Earth's motion through a luminiferous ether led to the development of special relativity, which corrects mechanics to handle situations involving motions nearing the speed of light. As of today, special relativity is the most accurate model of motion at any speed. Even so, Newtonian mechanics is still useful as an approximation at small velocities relative to the speed of light. Special relativity implies a wide range of consequences, which have been experimentally verified, including length contraction, time dilation, relativistic mass-energy equivalence, a universal speed limit, and relativity of simultaneity. It has replaced the conventional notion of an absolute universal time with the notion of a time that is dependent on reference frame and spatial position. Rather than an invariant time interval between two events, there is an invariant space-time interval. Combined with other laws of physics, the two postulates of special relativity predict the equivalence of mass and energy, as expressed in the mass-energy equivalence formula A equals mc2, where c is the speed of light in vacuum. A defining feature of special relativity is the replacement of the Galilean transformations of Newtonian mechanics with the Lorentz transformations. Time and space cannot be defined separately from one another. Rather, space and time are interwoven into a single continuum known as space-time. Events that occur at the same time for one observer could occur at different times for another. The theory is called special, because it applied the principle of relativity only to the special case of inertial reference frames. Einstein later published a paper on general relativity in 1915 to apply the principle in the general case, that is, to any frame so as to handle general coordinate transformations, and gravitational effects. As Galilean relativity is now considered an approximation of special relativity valid for low speeds, special relativity is considered an approximation of the theory of general relativity valid for weak gravitational fields. The presence of gravity becomes undetectable at sufficiently small scale, free-falling conditions. General relativity incorporates non-Euclidean geometry, so that the gravitational effects are represented by the geometric curvature of spacetime. Contrarily, special relativity is restricted to flat spacetime. The geometry of spacetime in special relativity is called Minkowski space. A locally Lorentz invariant frame that abides by special relativity can be defined at sufficiently small scales, even in curved spacetime. Galileo Galilei had already postulated that there is no absolute and well-defined state of rest, a principle now called Galileo's principle of relativity. Einstein extended this principle so that it accounted for the constant speed of light, a phenomenon that had been recently observed in the Michelson-Morley experiment. He also postulated that it holds for all the laws of physics, including both the laws of mechanics and of electrodynamics. Postulates: Einstein discerned two fundamental propositions that seem to be the most assured, regardless of the exact validity of the known laws of either mechanics or electrodynamics. These propositions were the constancy of the speed of light and the independence of physical laws from the choice of inertial system. In his initial presentation of special relativity in 1905 he expressed these postulates as, the principle of relativity the laws by which the states of physical systems undergo change are not affected, whether these changes of state be referred to the one or the other of two systems in uniform translatory motion relative to each other. The principle of invariant light speed Light is always propagated in empty space with a definite velocity, speed c, which is independent of the state of motion of the emitting body. That is, light in vacuum propagates with the speed c in at least one system of inertial coordinates, regardless of the state of motion of the light source. The derivation of special relativity depends not only on these two explicit postulates, but also on several tacit assumptions, including the isotropy and homogeneity of space and the independence of measuring rods and clocks from their past history. Following Einstein's original presentation of special relativity in 1905, many different sets of postulates have been proposed in various alternative derivations. However, the most common set of postulates remains those employed by Einstein in his original paper. A more mathematical statement of the principle of relativity made later by Einstein, which introduces the concept of simplicity not mentioned above, is special principle of relativity. If a system of coordinates k is chosen so that, in relation to it, physical laws hold good in their simplest form, the same laws hold good in relation to any other system of coordinates k moving in uniform translation relatively to k. Henri Poincaré copyright provided the mathematical framework for relativity theory by proving that Lorentz transformations are a subset of his Poincaré copyright group of symmetry transformations. Einstein later derived these transformations from his axioms. Many of Einstein's papers present derivations of the Lorentz transformation based upon these two principles. Einstein consistently based the derivation of Lorentz invariance on just the two basic principles of relativity and light speed invariance. He wrote, "The insight fundamental for the special theory of relativity is this: the assumptions relativity and light speed invariance are compatible if relations of a new type are postulated for the conversion of coordinates and times of events. The universal principle of the special theory of relativity is contained in the postulate, the laws of physics are invariant with respect to Lorentz transformations. This is a restricting principle for natural laws. Thus many modern treatments of special relativity base it on the single postulate of universal Lorentz covariance, or, equivalently, on the single postulate of Minkowski spacetime. From the principle of relativity alone without assuming the constancy of the speed of light one can show that the spacetime transformations between inertial frames are either Euclidean, Galilean, or Lorentzian. In the Lorentzian case, one can then obtain relativistic interval conservation and a certain finite limiting speed. Experiments suggest that this speed is the speed of light in vacuum. The constancy of the speed of light was motivated by Maxwell's theory of electromagnetism and the lack of evidence for the luminiferous ether. There is conflicting evidence on the extent to which Einstein was influenced by the null result of the Michelson-Euromorley experiment. In any case, the null result of the Michelson-Euromorley experiment helped the notion of the constancy of the speed of light gain widespread and rapid acceptance. Lack of an absolute reference frame. The principle of relativity, which states that there is no preferred inertial reference frame, dates back to Galileo, and was incorporated into Newtonian physics. However, in the late 19th century, the existence of electromagnetic waves led physicists to suggest that the universe was filled with a substance that they called ether, which would act as the medium through which these waves, or vibrations, traveled. The ether was thought to constitute an absolute reference frame against which speeds could be measured, and could be considered fixed and motionless. Ether supposedly possessed some wonderful properties. It was sufficiently elastic to support electromagnetic waves, and those waves could interact with matter, yet it offered no resistance to bodies passing through it. The results of various experiments, including the Michelson-Euromorley experiment, indicated that the Earth was always stationary relative to the ether, something that was difficult to explain, since the Earth is in orbit around the Sun. Einstein's solution was to discard the notion of an ether in the absolute state of rest. In relativity, any reference frame moving with uniform motion will observe the same laws of physics. In particular, the speed of light in vacuum is always measured to be c, even when measured by multiple systems that are moving at different velocities. Reference frames, coordinates and the Lorentz transformation. Relativity theory depends on reference frames. The term reference frame as used here is an observational perspective in space which is not undergoing any change in motion, from which a position can be measured along three spatial axes. In addition, a reference frame has the ability to determine measurements of the time of events using a clock. An event is an occurrence that can be assigned a single unique time and location in space relative to a reference frame. It is a point in space-time. Since the speed of light is constant in relativity in each and every reference frame, Pulses of light can be used to unambiguously measure distances and refer back the times that events occurred to the clock, even though light takes time to reach the clock after the event has transpired. For example, the explosion of a firecracker may be considered to be an event. We can completely specify an event by its four space-time coordinates, the time of occurrence and its three-dimensional spatial location define a reference point. Let's call this reference frame S. In relativity theory we often want to calculate the position of a point from a different reference point. Suppose we have a second reference frame z(r)2, whose spatial axis and clock exactly coincide with that of S at time 0, but it is moving at a constant velocity v with respect to S along the x-axis. Since there is no absolute reference frame in relativity theory, a concept of moving doesn't strictly exist, as everything is always moving with respect to some other reference frame. Instead, any two frames that move at the same speed in the same direction are said to be co-moving. Therefore S and z(r)2 are not co-moving. Define the event to have space-time coordinates in system S and in z(r)2. Then the Lorentz transformation specifies that these coordinates are related in the following way. Where is the Lorentz factor and c is the speed of light in vacuum, and the velocity v of z(r)2 is parallel to the x-axis. The y and z coordinates are unaffected. Only the x and t coordinates are transformed. These Lorentz transformations form a one-parameter group of linear mappings, that parameter being called rapidity. There is nothing special about the x-axis, the transformation can apply to the y or z-axis, or indeed in any direction, which can be done by directions parallel to the motion and perpendicular. See main article for details. A quantity invariant under Lorentz transformations is known as a Lorentz scalar. Writing the Lorentz transformation and its inverse in terms of coordinate differences, where for instance one event has coordinates and another event has coordinates and the differences are defined as we get. These effects are not merely appearances. They are explicitly related to our way of measuring time intervals between events which occur at the same place in a given coordinate system. These time intervals will be different in another coordinate system moving with respect to the first, unless the events are also simultaneous. Similarly, these effects also relate to our measured distances between separated but simultaneous events in a given coordinate system of choice. If these events are not co-local, but are separated by distance, they will not occur at the same spatial distance from each other when seen from another moving coordinate system. However, the space-time interval will be the same for all observers. The underlying reality remains the same. Only our perspective changes. Consequences derived from the Lorentz transformation. The consequences of special relativity can be derived from the Lorentz transformation equations. These transformations, and hence special relativity, led to different physical predictions than those of Newtonian mechanics when relative velocities become comparable to the speed of light. The speed of light is so much larger than anything humans encounter that some of the effects predicted by relativity are initially counterintuitive. Relativity of simultaneity. Two events happening in two different locations that occur simultaneously in the reference frame of one inertial observer, may occur non-simultaneously in the reference frame of another inertial observer. From the first equation of the Lorentz transformation in terms of coordinate differences, it is clear that two events that are simultaneous in frame S, are not necessarily simultaneous in another inertial frame z(r)2. Only if these events are additionally co-local in frame S, will they be simultaneous in another frame z(r)2. Time dilation. The time lapse between two events is not invariant from one observer to another, but is dependent on the relative speeds of the observer's reference frames. Suppose a clock is at rest in the unprimed system S. Two different ticks of this clock are then characterized by Ix equals 0. To find the relation between the times between these ticks as measured in both systems, the first equation can be used to find AAAA for event satisfying AAA. This shows that the time between the two ticks as seen in the frame in which the clock is moving, is longer than the time between these ticks as measured in the rest frame of the clock. Time dilation explains a number of physical phenomena. For example, the decay rate of muons produced by cosmic rays impinging on the Earth's atmosphere. Length contraction. The dimensions of an object as measured by one observer may be smaller than the results of measurements of the same object made by another observer. Similarly, suppose a measuring rod is at rest and aligned along the x-axis in the unprimed system S. In this system, the length of this rod is written as Ix. To measure the length of this rod in the system z(r)² in which the clock is moving, the distances z(r)² to the endpoints of the rod must be measured simultaneously in that system z(r)². In other words, the measurement is characterized by I(r)² equals 0, which can be combined with the fourth equation to find the relation between the lengths Ix and I z(r)², AAAA for event satisfying AAA. This shows that the length of the rod as measured in the frame in which it is moving, is shorter than its length in its own rest frame. Composition of velocities. Velocities do not simply add. If the observer in S measures an object moving along the x-axis at velocity u, then the observer in the z(r)² system, a frame of reference moving at velocity v in the x direction with respect to S, will measure the object moving with velocity v(r)² where the other frame S will measure. Notice that if the object were moving at the speed of light in the S system, then it would also be moving at the speed of light in the z(r)² system. Also, if both u and v are small with respect to the speed of light, we will recover the intuitive Galilean transformation of velocities. The usual example given is that of a train traveling due east with a velocity v with respect to the tracks. A child inside the train throws a baseball due east with a velocity v(r)² with respect to the train. In classical physics, an observer at rest on the tracks will measure the velocity of the baseball as u equals v(r)² plus v, while in special relativity this is no longer true. Instead, the velocity of the baseball is given by the second equation, u equals /1 plus v(r)² vc2. Again, there is nothing special about the x or east directions. This formalism applies to any direction by considering parallel and perpendicular motion to the direction of relative velocity v, see main article for details. Einstein's addition of collinear velocities is consistent with the Pfizer experiment which determined the speed of light in a fluid moving parallel to the light, but no experiment has ever tested the formula for the general case of non-parallel velocities. Other consequences, Thomas rotation. The orientation of an object may be different for different observers. Unlike other relativistic effects, this effect becomes quite significant at fairly low velocities as can be seen in the spin of moving particles. Equivalence of mass and energy. As an object's speed approaches the speed of light from an observer's point of view, its relativistic mass increases, thereby making it more and more difficult to accelerate it from within the observer's frame of reference. The energy content of an object at rest with mass m equals mc2. Conservation of energy implies that, in any reaction, a decrease of the sum of the masses of particles must be accompanied by an increase in kinetic energies of the particles after the reaction. Similarly, the mass of an object can be increased by taking in kinetic energies. In addition to the papers referenced ab v Euro, which give derivations of the Lorentz transformation and describe the foundations of special relativity Euro, Einstein also wrote at least 4 papers giving heuristic arguments for the equivalence of mass and energy, for E equals mc2. Massa Euro energy equivalence is a consequence of special relativity. The energy and momentum, which are separate in Newtonian mechanics, form a 4-vector in relativity, and this relates the time component to the space components in a non-trivial way. For an object at rest, the energy Euro momentum 4-vector is, it has a time component which is the energy, and 3 space components which are 0. By changing frames with the Lorentz transformation in the x direction with a small value of the velocity v, the energy momentum 4-vector becomes. The momentum is equal to the energy multiplied by the velocity divided by c2. As such, the Newtonian mass of an object, which is the ratio of the momentum to the velocity for slow velocities, is equal to ec2. The energy and momentum are properties of matter and radiation, and it is impossible to deduce that they form a 4-vector just from the 2 basic postulates of special relativity by themselves. Because these don't talk about matter or radiation, they only talk about space and time. The derivation therefore requires some additional physical reasoning. In his 1905 paper, Einstein used the additional principles that Newtonian mechanics should hold for slow velocities, so that there is one energy scalar and one three-vector momentum at slow velocities, and that the conservation law for energy and momentum is exactly true in relativity. Furthermore, he assumed that the energy of light is transformed by the same Doppler shift factor as its frequency, which he had previously shown to be true based on Maxwell's equations. The first of Einstein's papers on this subject was Does the inertia of a body depend upon its energy content? In 1905. Although Einstein's argument in this paper is nearly universally accepted by physicists as correct, even self-evident, many authors over the years have suggested that it is wrong. Other authors suggest that the argument was merely inconclusive because it relied on some implicit assumptions. Einstein acknowledged the controversy over his derivation in his 1907 survey paper on special relativity. There he notes that it is problematic to rely on Maxwell's equations for the heuristic mass-energy argument. The argument in his 1905 paper can be carried out with the emission of any massless particles, but the Maxwell equations are implicitly used to make it obvious that the emission of light in particular can be achieved only by doing work. To emit electromagnetic waves, all you have to do is shake a charged particle, and this is clearly doing work, so that the emission is of energy. How far can one travel from the Earth? Since one cannot travel faster than light, one might conclude that a human can never travel further from Earth than 40 light-years if the traveler is active between the age of 20 and 60. One would easily think that a traveler would never be able to reach more than the very few solar systems which exist within the limit of 40 light-years from the Earth. But that would be a mistaken conclusion. Because of time dilation, a hypothetical spaceship can travel thousands of light-years during the pilot's 40 active years. If a spaceship could be built that accelerates at a constant 1g, it will after a little less than a year be traveling at almost the speed of light as seen from Earth. Time dilation will increase his lifespan as seen from the reference system of the Earth, but his lifespan measured by a clock traveling with him will not thereby change. During his journey, people on Earth will experience more time than he does. A 5-year round trip for him will take 6½ Earth years and cover a distance of over 6 light years. A 20-year round trip for him will land him back on Earth having traveled for 335 Earth years and a distance of 331 light years. A full 40-year trip at 1g will appear on Earth to last 58,000 years and cover a distance of 55,000 light years. A 40-year trip at 1.1g will take 148,000 Earth years and cover about 140,000 light years. A one-way 28-year trip at 1g acceleration could reach 2 million light-years to the Andromeda Galaxy. This same time dilation is why a muon traveling close to C is observed to travel much further than C times its half-life. Causality and prohibition of motion faster than light. In diagram 2 the interval AB is time-like. That is, there is a frame of reference in which events A and B occur at the same location in space, separated only by occurring at different times. If A precedes B in that frame, then A precedes B in all frames. It is hypothetically possible for matter to travel from A to B, so there can be a causal relationship. The interval AC in the diagram is space-like. That is, there is a frame of reference in which events A and C occur simultaneously, separated only in space. There are also frames in which A precedes C and frames in which C precedes A. If it were possible for a cause and effect relationship to exist between events A and C, then paradoxes of causality would result. For example, if A was the cause, and C the effect, then there would be frames of reference in which the effect preceded the cause. Although this in itself won't give rise to a paradox, one can show that faster-than-light signals can be sent back into one's own past. A causal paradox can then be constructed by sending the signal if and only if no signal was received previously. Therefore, if causality is to be preserved, One of the consequences of special relativity is that no information signal or material object can travel faster than light in vacuum. However, some things can still move faster than light. For example, the location where the beam of a searchlight hits the bottom of a cloud can move faster than light when the searchlight is turned rapidly. Even without considerations of causality, there are other strong reasons why faster-than-light travel is forbidden by special relativity. For example, if a constant force is applied to an object for a limitless amount of time, then integrating F equals dp dt gives a momentum that grows without bound, but this is simply because approaches infinity as approaches c. To an observer who is not accelerating, it appears as though the object's inertia is increasing, so as to produce a smaller acceleration in response to the same force. This behavior is observed in particle accelerators, where each charged particle is accelerated by the electromagnetic force. Theoretical and experimental tunneling studies carried out by Garwan-Korter-N.T.R. Nimtz and Patricia Eckel claim that under special conditions signals may travel faster than light. It was measured that fiber digital signals were traveling up to 5 times c, and a zero-time tunneling electron carried the information that the atom is ionized, with photons, phonons and electrons spending zero time in the tunneling barrier. According to Nimtz and Eckel, in this superluminal process only the Einstein causality and the special relativity but not the primitive causality are violated. Superluminal propagation does not result in any kind of time travel. Several scientists have stated not only that Nimtz's interpretations were erroneous, but also that the experiment actually provided a trivial experimental confirmation of the special relativity theory. Geometry of spacetime. Comparison between flat Euclidean space and Minkowski space. Special relativity uses a flat four-dimensional Minkowski spatial an example of a spacetime. Minkowski spacetime appears to be very similar to the standard three-dimensional Euclidean space, but there is a crucial difference with respect to time. In 3D space, the differential of distance ds is defined by where dx equals are the differentials of the three spatial dimensions. In Minkowski geometry, there is an extra dimension with coordinate xo derived from time, such that the distance differential fulfills where dx equals are the differentials of the four spacetime dimensions. This suggests a deep theoretical insight. Special relativity is simply a rotational symmetry of our spacetime, analogous to the rotational symmetry of Euclidean space. Just as Euclidean space uses a Euclidean metric, so spacetime uses a Minkowski metric. Basically, special relativity can be stated as the invariance of any spacetime interval when viewed from any inertial reference frame. All equations and effects of special relativity can be derived from this rotational symmetry of Minkowski spacetime. The actual form of ds above depends on the metric and on the choices for the xo coordinate. To make the time coordinate look like the space coordinates, it can be treated as imaginary, xo equals ict. According to Misner, Thorne and Wheeler, ultimately the deeper understanding of both special and general relativity will come from the study of the Minkowski metric and to take xo equals ct, rather than a disguised Euclidean metric using it as the time coordinate. Some authors use xo equals t, with factors of c elsewhere to compensate. For instance, spatial coordinates are divided by c, or factors of k plus or minus 2 are included in the metric tensor. These numerous conventions can be superseded by using natural units where c equals 1. Then space and time have equivalent units, and no factors of c appear anywhere. 3D spacetime. If we reduce the spatial dimensions to 2, so that we can represent the physics in a 3D space, we see that the null geodesics lie along a dual cone defined by the equation. Or simply, a Euro-sheet is the equation of a circle of radius k dt. 4D spacetime, if we extend this to 3 spatial dimensions, the null geodesics are the 4-dimensional cone. So, this null dual cone represents the line of sight of a point in space. That is, when we look at the stars and say the light from that star which I am receiving is x years old, we are looking down this line of sight, a null geodesic. We are looking at an event a distance away and a time dc in the past. For this reason the null dual cone is also known as the light cone. The cone in the AT region is the information that the point is receiving, while the cone in the plus T section is the information that the point is sending. The geometry of Minkowski space can be depicted using Minkowski diagrams, which are useful also in understanding many of the thought experiments in special relativity. Note that, in 4D space-time, the concept of the center of mass becomes more complicated, see center of mass. Physics in space-time, transformations of physical quantities between reference frames, above. The Lorentz transformation for the time coordinate and 3 space coordinates illustrates that they are intertwined. This is true more generally. Certain pairs of time-like, and space-like quantities naturally combine on equal footing under the same Lorentz transformation. The Lorentz transformation in standard configuration above, that is for a boost in the x direction, can be recast into matrix form as follows. In Newtonian mechanics, quantities which have magnitude and direction are mathematically described as 3D vectors in Euclidean space, and in general they are parametrized by time. In special relativity, this notion is extended by adding the appropriate time-like quantity to a space-like vector quantity, and we have 4D vectors, or 4 vectors, in Minkowski space-time. The components of vectors are written using tensor index notation, as this has numerous advantages. The notation makes it clear the equations are manifestly covariant under the Poincare copyright group, thus bypassing the tedious calculations to check this fact. In constructing such equations, we often find that equations previously thought to be unrelated are, in fact, closely connected, being part of the same tensor equation. Recognizing other physical quantities as tensors simplifies their transformation laws. Throughout, upper indices are contravariant indices rather than exponents except when they indicate a square, and lower indices are covariant indices. For simplicity and consistency with the earlier equations, Cartesian coordinates will be used. The simplest example of a 4-vector is the position of an event in space-time, which constitutes a time-like component ct and space-like component x equals, in a contravariant position 4-vector with components. Where we define xo equals ct so that the time coordinate has the same dimension of distance as the other spatial dimensions, so that space and time are treated equally. Now the transformation of the contravariant components of the position 4-vector can be compactly written as, where there is an implied summation on I1/2 from 0 to 3, and is a matrix. More generally, all contravariant components of a 4-vector transform from one frame to another frame by a Lorentz transformation. Examples of other 4-vectors include the 4-velocity E1/4, defined as the derivative of the position 4-vector with respect to proper time, where the Lorentz factor is the relativistic energy and relativistic momentum of an object are respectively the time-like and space-like components of a covariant 4-momentum vector, where m is the invariant mass. The 4-acceleration is the proper time derivative of 4-velocity. The transformation rules for 3-dimensional velocities and accelerations are very awkward. Even above in standard configuration the velocity equations are quite complicated owing to their nonlinearity. On the other hand, the transformation of 4-velocity and 4-acceleration are simpler by means of the Lorentz transformation matrix. The 4-gradient of a scalar field I transforms covariantly rather than contravariantly. That is, only in Cartesian coordinates. It's the covariant derivative which transforms in manifest covariance. In Cartesian coordinates this happens to reduce to the partial derivatives, but not in other coordinates. More generally, the covariant components of a 4-vector transform according to the inverse Lorentz transformation. Where is the reciprocal matrix of? The postulates of special relativity constrain the exact form the Lorentz transformation matrices take. More generally, most physical quantities are best described as tensors. So to transform from one frame to another, we use the well-known tensor transformation law. Where is the reciprocal matrix of? All tensors transform by this rule. An example of a 4-dimensional second-order antisymmetric tensor is the relativistic angular momentum, which has 6 components, 3 are the classical angular momentum, and the other 3 are related to the boost of the center of mass of the system. The derivative of the relativistic angular momentum with respect to proper time is the relativistic torque, also second-order antisymmetric tensor. The electromagnetic field tensor is another second-order antisymmetric tensor field, with 6 components, 3 for the electric field and another 3 for the magnetic field. There is also the stressor-energy tensor for the electromagnetic field, namely the electromagnetic stressor-energy tensor. Metric: the metric tensor allows one to define the inner product of 2 vectors, which in turn allows one to assign a magnitude to the vector. Given the 4-dimensional nature of spacetime, the Minkowski metric I has components which can be arranged in a 4 matrix, which is equal to its reciprocal, in those frames. Throughout we use the signs as above. Different authors use different conventions. See Minkowski metric alternative signs. The Poincaré copyright group is the most general group of transformations which preserves the Minkowski metric. And this is the physical symmetry underlying special relativity. The metric can be used for raising and lowering indices on vectors and tensors. Invariants can be constructed using the metric, the inner product of a 4-vector T with another 4-vector S's. Invariant means that it takes the same value in all inertial frames, because it is a scalar, and so no I appears in its trivial transformation. The magnitude of the 4-vector T is the positive square root of the inner product with itself. One can extend this idea to tensors of higher order. For a second-order tensor we can form the invariants. Similarly for higher-order tensors. Invariant expressions, particularly inner products of 4 vectors with themselves, provide equations that are useful for calculations, because one doesn't need to perform Lorentz transformations to determine the invariants. Relativistic kinematics and invariants, the coordinate differentials transform also contravariantly. So the squared length of the differential of the position 4-vector d psi 1/4 constructed using is an invariant. Notice that when the line element dx2 is negative, that a SHA dx2 is the differential of proper time, while when dx2 is positive, a sh dx2 is differential of the proper distance. The 4-velocity e1/4 has an invariant form, which means all velocity 4 vectors have a magnitude of c. This is an expression of the fact that there is no such thing as being at coordinate rest in relativity. At the least, you are always moving forward through time. Differentiating the above equation by I produces. So in special relativity, the acceleration 4-vector and the velocity 4-vector are orthogonal. Relativistic dynamics and invariants, the invariant magnitude of the momentum 4-vector generates the energia-momentum relation. We can work out what this invariant is by first arguing that, since it is a scalar, it doesn't matter in which reference frame we calculate it, and then by transforming to a frame where the total momentum is 0. We see that the rest energy is an independent invariant. A rest energy can be calculated even for particles and systems in motion, by translating to a frame in which momentum is 0. The rest energy is related to the mass according to the celebrated equation discussed above. Note that the mass of systems measured in their center of momentum frame is given by the total energy of the system in this frame. It may not be equal to the sum of individual system masses measured in other frames. To use Newton's third law of motion, both forces must be defined as the rate of change of momentum with respect to the same time coordinate. That is, it requires the 3D force defined above. Unfortunately, there is no tensor in 4D which contains the components of the 3D force vector among its components. If a particle is not traveling at c, one can transform the 3D force from the particle's co-moving reference frame into the observer's reference frame. This yields a 4-vector called the 4-force. It is the rate of change of the above energy momentum 4-vector with respect to proper time. The covariant version of the 4-force is in the rest frame of the object, the time component of the 4-force is 0 unless the invariant mass of the object is changing, in which case it is the negative of that rate of change of mass, times c. In general, though, the components of the 4-force are not equal to the components of the 3-force, because the three forces defined by the rate of change of momentum with respect to coordinate time, that is dp dt, while the fourth force is defined by the rate of change of momentum with respect to proper time, that is dpd. In a continuous medium, the 3D density of force combines with the density of power to form a covariant 4-vector. The spatial part is the result of dividing the force on a small cell by the volume of that cell. The time component is a 1 per carat times the power transferred to that cell divided by the volume of the cell. This will be used below in the section on electromagnetism. Relativity and unifying electromagnetism. Theoretical investigation in classical electromagnetism led to the discovery of wave propagation. Equations generalizing the electromagnetic effects found that finite propagation speed of the E and B fields required certain behaviors on charged particles. The general study of moving charges forms the Lear-copyright-Nada-Wiechert potential, which is a step towards special relativity. The Lorentz transformation of the electric field of a moving charge into a non-moving observer's reference frame results in the appearance of a mathematical term commonly called the magnetic field. Conversely, the magnetic field generated by a moving charge disappears and becomes a purely electrostatic field in a co-moving frame of reference. Maxwell's equations are thus simply an empirical fit to special relativistic effects in a classical model of the universe. As electric and magnetic fields are reference frame dependent and thus intertwined, one speaks of electromagnetic fields. Special relativity provides the transformation rules for how an electromagnetic field in one inertial frame appears in another inertial frame. Maxwell's equations in the 3D form are already consistent with the physical content of special relativity, although they are easier to manipulate in a manifestly covariant form, that is in the language of tensor calculus. See main links for more detail. Status. Special relativity in its Minkowski spacetime is accurate only when the absolute value of the gravitational potential is much less than c2 in the region of interest. In a strong gravitational field, one must use general relativity. General relativity becomes special relativity at the limit of weak field. At very small scales, such as at the Planck length and below, quantum effects must be taken into consideration resulting in quantum gravity. However, at macroscopic scales and in the absence of strong gravitational fields, special relativity is experimentally tested to extremely high degree of accuracy and thus accepted by the physics community. Experimental results which appear to contradict it are not reproducible and are thus widely believed to be due to experimental errors. Special relativity is mathematically self-consistent, and it is an organic part of all modern physical theories, most notably quantum field theory, string theory, and general relativity. Newtonian mechanics mathematically follows from special relativity at small velocities thus Newtonian mechanics can be considered as a special relativity of slow-moving bodies. See classical mechanics for a more detailed discussion. Several experiments predating Einstein's 1905 paper are now interpreted as evidence for relativity. Of these it is known Einstein was aware of the Pfizer experiment before 1905, and historians have concluded that Einstein was at least aware of the Michelson-Morley experiment as early as 1899 despite claims he made in his later years that it played no role in his development of the theory. The Pfizer experiment measured the speed of light in moving media, with results that are consistent with relativistic addition of collinear velocities. The famous Michelson-Morley experiment gave further support to the postulate that detecting an absolute reference velocity was not achievable. It should be stated here that, contrary to many alternative claims, it said little about the invariance of the speed of light with respect to the source and observer's velocity, as both source and observer were traveling together at the same velocity at all times. The Troughton-Noble experiment showed that the torque on a capacitor is independent of position and inertial reference frame. The experiments of Rayleigh and Brace showed that length contraction doesn't lead to birefringence for a co-moving observer, in accordance with the relativity principle. Particle accelerators routinely accelerate and measure the properties of particles moving at near the speed of light, where their behavior is completely consistent with relativity theory and inconsistent with the earlier Newtonian mechanics. These machines would simply not work if they were not engineered according to relativistic principles. In addition, a considerable number of modern experiments have been conducted to test special relativity. Some examples: tests of relativistic energy and momentum testing the limiting speed of particles, Pfizer Stilwell experiment testing relativistic Doppler effect and time dilation of moving particles relativistic effects on a fast-moving particle's half-life, Kendia Thorndike experiment time dilation in accordance with Lorentz transformations, Heiser Drever experiment testing isotropy of space and mass, modern searches for Lorentz violation various modern tests. Experiments to test emission theory demonstrated that the speed of light is independent of the speed of the emitter. Experiments to test the ether drag hypothesis no ether flow obstruction. Theories of relativity in quantum mechanics. Special relativity can be combined with quantum mechanics to form relativistic quantum mechanics. It is an unsolved problem in physics how general relativity and quantum mechanics can be unified. Quantum gravity and a theory of everything, which require such a unification, are active and ongoing areas in theoretical research. The early Bohr-Sommerfeld atomic model explained the fine structure of alkali metal atoms using both special relativity and the preliminary knowledge on quantum mechanics of the time. In 1928, Paul Dirac constructed an influential relativistic wave equation, now known as the Dirac equation in his honor, that is fully compatible both with special relativity and with the final version of quantum theory existing after 1926. This equation explained not only the intrinsic angular momentum of the electrons called spin, it also led to the prediction of the antiparticle of the electron, and fine structure could only be fully explained with special relativity. It was the first foundation of relativistic quantum mechanics. In non-relativistic quantum mechanics, spin is phenomenological and cannot be explained. On the other hand, the existence of antiparticles leads to the conclusion that relativistic quantum mechanics is not enough for a more accurate and complete theory of particle interactions. Instead, a theory of particles interpreted as quantized fields, called quantum field theory, becomes necessary, in which particles can be created and destroyed throughout space and time. See also: People, Hendrik Lorentz Henri Poincaré Copyright Albert Einstein Max Planck Hermann Minkowski Max von Laue Arnold Sommerfeld Max Born Gustav Herglotz Richard C. Tolman, Relativity, Theory of Relativity History of Special Relativity Principle of Relativity General Relativity Frame of Reference Inertial Frame of Reference Lorentz Transformations Bond-decay Calculus Einstein Synchronization Riot Dija Putnam Argument Special Relativity Criticism of Relativity Theory Relativity Priority Dispute, Physics, Newtonian Mechanics Space-time Speed of Light Simultaneity Center of Mass Physical Cosmology Doppler Effect Relativistic Euler Equations Ether Drag Hypothesis Lorentz Ether Theory Moving Magnet and Conductor Problem Shape Waves Relativistic Heat Conduction Relativistic Disk Thomas Precession Born Rigidity Born Coordinates, Mathematics, Derivations of the Lorentz Transformations Minkowski Space 4 Vector World Line Light Cone Lorentz Group Poincaré Copyright Group Geometry Tensors Split Complex Number Relativity in the APS Formalism, Philosophy, Actualism Conventionalism Formalism, Paradoxes, Twin Paradox Arianfest Paradox Ladder Paradox Bell's Spaceship Paradox Velocity Composition Paradox, References. Textbooks, Einstein, Albert. Relativity, the Special and General Theory. Einstein, Albert. The Meaning of Relativity. Fine Communications. ISBN 1-56731-136-9, Uganov, Anatoly Henri Poincaré Copyright and the Relativity Theory Nauka, Moscow. Charles Misner, Kip Thorne, and John Archibald Wheeler Gravitation W. H. Freeman and Company. ISBN 0-7167-0334-3, Post, E.J., 1997 Formal Structure of Electromagnetics, General Covariance and Electromagnetics. Dover Publications. Wolfgang Rieneler. Introduction to Special Relativity, Oxford University Press. ISBN 978-0-19-853952-0. ISBN 0-19-853952-5. Harvey R. Brown. Physical Relativity, Spatio-Euro-Time Structure from a Dynamical Perspective, Oxford University Press, ISBN 0-927583-1. ISBN 978-0-19-927583-0. Kadir, ASGHAR. Relativity, An Introduction to the Special Theory. Singapore, World Scientific Publications. PA 128. ISBN A9971-5-0612-2. Silberstein, Ludwig. The Theory of Relativity. Lorentz Scalar. Space, Time and Space-Time. University of California Press. ISBN A0-520-03174-1. Lorentz Scalar. Philosophy of Physics. Westview Press. ISBN A0-8133-0625-6. Taylor, Edwin, and John Archibald Wheeler. Space-Time Physics. W. H. Freeman and Company. ISBN 0-7167-2327-1. Tipler, Paul, and Llewellyn, Ralph. Modern Physics. W. H. Freeman and Company. ISBN 0-7167-4345-0. Journal articles, Alvager, A. al. Farley, F. J. M. Kjelman, J. Wallin, L. Test of the second postulate of special relativity in the GeV region. Physics Letter 12, 260. Bibcode, 1964 PHL, 12260A doi, 10.1016/0031-9163, 64, 91095-9. D'Arigel, Olivier. The Mystery of the Poincaré v. Euro-Einstein Connection. Assis 95, 614 Euro 26 doi, 10.1086/430652. PMIDA 16011297. Wolf, Peter. Petty, Gerard. Satellite Test of Special Relativity Using the Global Positioning System. Physical Review of 56, 4405 Euro 09. Bibcode, 1997 PHRVA 56.4405W doi, 10.1103/physrev A 56.4405. External links, original works, Zur Electrodynamik Bewegter Car Paragraph. Per Einstein's original work in German, Annalen der Physik, Bern 1905, on the Electrodynamics of Moving Bodies. English translation as published in the 1923 book The Principle of Relativity. Special Relativity for a General Audience, Wikibooks, Special Relativity, Einstein Light. An award-winning, non-technical introduction supported by dozens of pages of further explanations and animations, at levels with or without mathematics. Einstein Online Introduction to Relativity Theory, from the Max Planck Institute for Gravitational Physics. Audio, Kane Gayer Euroastronomy Cast. Einstein's Theory of Special Relativity, Special Relativity Explained, Greg Egan's Foundations. The Hogg Notes on Special Relativity. A good introduction to special relativity at the undergraduate level, using calculus. Relativity Calculator, Special Relativity. An algebraic and integral calculus derivation for E equals MC2. Math Pages. Reflections on Relativity. A complete online book on relativity with an extensive bibliography. Relativity. An introduction to special relativity at the undergraduate level, without calculus. Relativity, the Special and General Theory at Project Gutenberg, by Albert Einstein. Special Relativity Lecture Notes is a standard introduction to special relativity containing illustrative explanations based on drawings and space-time diagrams from Virginia Polytechnic Institute and State University. Understanding Special Relativity. The Theory of Special Relativity in an Easily Understandable Way. An Introduction to the Special Theory of Relativity by Robert Katz, an introduction that is accessible to any student who has had an introduction to general physics and some slight acquaintance with the calculus. Lecture Notes on Special Relativity by J. D. Kresser, Department of Physics, Macquarie University. SpecialRelativity.net, an overview with visualizations and minimal mathematics. Visualization, ray tracing special relativity software visualizing several scenarios under the influence of special relativity. Real-time relativity, the Australian National University. Relativistic visual effects experienced through an interactive program. Space-time travel, a variety of visualizations of relativistic effects, from relativistic motion to black holes. Through Einstein's eyes, the Australian National University. Relativistic visual effects explained with movies and images. Warp Special Relativity Simulator, a computer program to show the effects of traveling close to the speed of light. Animation clip visualizing the Lorentz transformation. Original interactive flash animations from John DePillis illustrating Lorentz and Galilean frames, train and tunnel paradox, the twin paradox, wave propagation, clock synchronization, etc. Relativistic optics at the ANU, Lightspeed, an OpenGL-based program developed to illustrate the effects of special relativity on the appearance of moving objects. Animation showing the stars near Earth, as seen from a spacecraft accelerating rapidly to light speed.